Picture this, a vast cosmic neighborhood, home to thousands of galaxies, each one a swirling island of stars, gas, and dust. Now imagine that within this colossal gathering of galaxies, there are secrets so profound, so baffling, that even the brightest minds on Earth are left scratching their heads. Welcome to the Virgo Cluster, the largest galaxy cluster in our corner of the universe, and a treasure trove of cosmic mysteries waiting to be unraveled. In this video, we're diving deep into 25 unexplained phenomena that defy our understanding of the cosmos. From galaxies that seem to vanish into thin air to supermassive black holes behaving in ways that shouldn't be possible, the Virgo Cluster is a place where the rules of physics are rewritten and the universe reveals its most enigmatic side. These aren't just scientific curiosities, they're clues that could reshape everything we think we know about space, time, and the very fabric of reality. So, if you've ever looked up at the night sky and wondered what lies beyond the stars, you're in for a journey like no other. By the end of this video, you'll not only have a front row seat to some of the most perplexing cosmic puzzles, but also a glimpse into the questions that keep astronomers awake at night. Ready to explore the unknown, let's begin. Now, let's turn our attention to the first of these cosmic enigmas, the missing dark matter galaxy. Imagine a galaxy that defies one of the most fundamental principles of modern astrophysics. Meet NGC 1052DF2, a galaxy in the Virgo cluster that has left scientists utterly baffled. Unlike most galaxies, which are thought to be held together by the gravitational pull of dark matter, this one appears to have almost none of it. Discovered in 2018, NGC 1052DF2 immediately stood out as an anomaly. Dark matter, which makes up about 85% of the universe's mass, is believed to be the invisible scaffolding that holds galaxies together. Without it, galaxies like ours would simply fly apart, but this galaxy seems to challenge that idea. Observations show that its stars move at speeds that can only be explained if dark matter is absent, or at least present in far smaller amounts than expected. This discovery has sparked heated debates among scientists. Some argue that NGC 1052DF2 could be a rare exception, a galaxy that formed under unique conditions. Others suggest that our understanding of dark matter might need a serious rethink. Could there be alternative explanations for how galaxies form and evolve? Or is this a sign that dark matter behaves in ways we don't yet understand? The implications are profound. If dark matter isn't as universal as we thought, it could shake the very foundations of astrophysics. It's a reminder that even our most well-established theories are open to question, and that the universe always has more surprises in store. As we move forward, keep this galaxy in mind. It's just the first of many mysteries we'll uncover in the Virgo cluster. Next, we'll explore another head-scratcher, the cluster's supermassive black holes and the strange patterns they've revealed. Now, let's dive into another fascinating mystery lurking within the Virgo cluster, the supermassive black hole enigma. This region of space is home to an unusually high number of these cosmic giants, and their behavior has left scientists scratching their heads. Supermassive black holes are typically found at the centers of galaxies, but in the Virgo cluster, they seem to be everywhere, and their distribution doesn't quite match what we'd expect. Recent observations have revealed that these black holes are not only more numerous than anticipated, but also exhibit strange patterns in their activity. Some are incredibly active, devouring surrounding matter and spewing out jets of energy, while others appear eerily quiet, as if they've gone dormant. This inconsistency raises a big question. Why are these supermassive black holes behaving so differently, even within the same cluster? One theory suggests that the dense environment of the Virgo cluster might be playing a role. With so many galaxies packed closely together, interactions between them could be triggering unusual activity in their central black holes. For example, when galaxies collide or pass near each other, their black holes might merge or be flung into new orbits, creating chaotic and unpredictable behavior. Another possibility is that we're seeing the effects of dark matter. Some scientists speculate that dark matter could be influencing the distribution and activity of these black holes in ways we don't yet fully understand. Could dark matter be funneling material towards certain black holes, making them more active, or is it somehow suppressing activity in others? What's clear is that the Virgo Cluster's supermassive black holes are challenging our understanding of how these cosmic monsters form and evolve. They're forcing us to rethink our models and consider new possibilities. And as we continue to study them, we're reminded once again that the universe is far more complex and far more mysterious than we ever imagined. As we move forward, let's shift our focus to another intriguing phenomenon, the enigmatic dark flow within the Virgo Cluster, where galaxies seem to be moving in a way that defies explanation. Now, let's turn our attention to one of the most puzzling mysteries in the Virgo Cluster, the enigmatic dark flow. Imagine looking out at a river and noticing that all the water is flowing in one direction, defying the natural landscape around it. That's the kind of baffling phenomenon astronomers have observed here, but instead of water, it's entire galaxies moving together in a way that shouldn't be possible. This mysterious cosmic flow was first detected when scientists noticed that hundreds of galaxies within the Virgo Cluster were drifting in the same direction at incredible speeds, up to millions of miles per hour. What's even more intriguing is that this motion doesn't align with the expected gravitational pull of the cluster itself. It's as if some unseen force is tugging these galaxies along, guiding them toward a point far beyond the edges of the observable universe. So, what could be causing this strange movement? One leading theory suggests that the dark flow might be influenced by massive structures outside our observable universe, regions so distant that their light hasn't had time to reach us yet. These structures, possibly made up of vast concentrations of matter or even other galaxy clusters, could be exerting a gravitational pull strong enough to affect the Virgo Cluster's galaxies. Another possibility is that the dark flow is a remnant of the early universe, a kind of cosmic echo from the Big Bang. During the universe's infancy, rapid expansion could have created ripples in space-time, and these ripples might still be influencing the motion of galaxies today. If true, this would provide a rare glimpse into the conditions of the universe just moments after its birth. But here's the catch: if the dark flow is real, it challenges one of the fundamental principles of cosmology, the idea that the universe is uniform on large scales. This phenomenon suggests that there might be vast, unseen structures or forces at play, reshaping our understanding of the cosmos. As we continue to study the dark flow, we're left with more questions than answers. What lies beyond the observable universe that's pulling these galaxies? Could this be evidence of a multiverse or something even more extraordinary? For now, the dark flow remains one of the most tantalizing mysteries in the Virgo Cluster, reminding us that the universe is full of secrets waiting to be uncovered. Next, we'll explore another astonishing feature of the Virgo Cluster: its massive radio halo, a phenomenon that challenges our understanding of how galaxy clusters evolve and interact. Now, let's shift our gaze to another extraordinary feature of the Virgo Cluster, its colossal radio halo. Picture a faint, glowing ring of light surrounding a galaxy cluster, but instead of visible light, this halo emits radio waves, a phenomenon that has left scientists both fascinated and perplexed. The Virgo Cluster's radio halo is one of the largest and most energetic structures of its kind ever observed. Stretching across millions of light-years, this immense halo is made up of charged particles spiraling through magnetic fields, producing radio emissions that can be detected by powerful telescopes. What makes this halo so remarkable is not just its size, but the sheer amount of energy it radiates, energy that defies our current understanding of how galaxy clusters behave. So, how does such a massive radio halo form? One leading theory suggests that it's the result of violent cosmic events, such as collisions between galaxies or the explosive activity of supermassive black holes. These events can accelerate particles to nearly the speed of light, creating shockwaves that ripple through the cluster's gas and magnetic fields. Over time, these shockwaves could generate the vast radio emissions we observe today. But here's where things get even more intriguing. The energy required to sustain such a massive radio halo is far greater than what current astrophysical models predict. According to our understanding, the energy from galaxy collisions and black hole activity should dissipate much faster than it appears to in the Virgo cluster. This discrepancy has led scientists to question whether there's an additional, unknown source of energy at play, or if our models of galaxy cluster dynamics are missing a crucial piece of the puzzle. Another mystery lies in the halo's structure. Unlike other radio halos, which tend to be more uniform, the Virgo cluster's halo shows complex patterns and variations in brightness. These irregularities suggest that the halo's formation and evolution are influenced by multiple factors, from the cluster's turbulent history to the intricate interplay of magnetic fields and cosmic rays. As we continue to study this enigmatic radio halo, it raises profound questions about the nature of galaxy clusters and the forces that shape them. Could this halo be evidence of new physics, or is it simply revealing gaps in our current knowledge? For now, the Virgo cluster's radio halo stands as a testament to the universe's ability to surprise us, reminding us that even the most well-studied regions of space still hold secrets waiting to be uncovered. Next, we'll delve into another fascinating mystery, the strange behavior of M87's jet, a cosmic phenomenon that continues to baffle astronomers. Now, let's turn our attention to one of the most striking features of the Virgo cluster, the bizarre jet of particles streaming from the supermassive black hole at the heart of M87. This jet, stretching over 5,000 light-years into space, is a cosmic spectacle that has puzzled astronomers for decades. At the center of M87 lies a supermassive black hole, one of the most massive ever discovered. This black hole doesn't just sit quietly, it's an active powerhouse, spewing out a jet of particles at nearly the speed of light. What makes this jet so unusual is its structure. Unlike most jets, which are relatively straight and uniform, M87's jet twists and bends in ways that defy expectations. Scientists believe the jet is formed as material spirals into the black hole, creating a swirling disk of gas and dust. Some of this material gets funneled into powerful magnetic fields, which launch it outward in two opposing streams. But here's the mystery: why does this jet appear to wobble and curve? Some theories suggest that the black hole's spin or the surrounding magnetic fields could be causing these distortions. Others propose that interactions with nearby gas clouds or even the cluster's environment might be playing a role. Adding to the intrigue, the jet emits light across the electromagnetic spectrum, from radio waves to gamma rays. This multi-wavelength emission provides clues about the jet's composition and the extreme conditions near the black hole. Yet, despite decades of observation, the exact mechanisms driving the jet's formation and behavior remain unclear. One of the most baffling aspects is the jet's brightness. At certain points along its length, the jet flares up unexpectedly, releasing bursts of energy that outshine even the black hole itself. These flares could be caused by shock waves within the jet or by collisions with material in its path, but their exact origins are still a matter of debate. The jet's unusual behavior challenges our understanding of how supermassive black holes interact with their surroundings. It raises questions about the role of magnetic fields, the dynamics of accretion disks, and even the nature of space-time itself. Could this jet be revealing new physics, or is it simply highlighting gaps in our current models? As we continue to study M87's jet, it serves as a reminder of the complexity and unpredictability of the universe. This cosmic enigma not only captivates our curiosity, but also pushes the boundaries of what we know about the most extreme environments in space. Next, we'll explore another mystery lurking in the Virgo cluster, the missing baryons, a puzzle that has left scientists searching for answers about the fate of ordinary matter in the cosmos. Now, shifting our gaze to another cosmic puzzle, we encounter the mystery of the Virgo cluster's missing baryons. Baryons, the building blocks of ordinary matter, make up everything we can see: stars, planets, gas, and even ourselves. Yet, when scientists tally up the expected amount of baryons in the Virgo cluster, a significant portion seems to have vanished. This discrepancy, known as the missing baryon problem, has left astronomers scratching their heads and searching for answers. The Virgo cluster, like other galaxy clusters, is thought to contain vast amounts of baryonic matter in the form of hot gas, stars, and galaxies. However, observations reveal that only about half of the predicted baryons are accounted for. Where could the rest be hiding? One leading theory suggests that the missing baryons might exist in a diffuse, hard-to-detect form, such as warm, hot intergalactic gas. This gas, spread thinly between galaxies, could be so faint that it escapes detection by traditional telescopes. To uncover this elusive matter, scientists have turned to innovative techniques. For instance, they use X-ray telescopes to search for faint emissions from the warm, hot gas, or they study the way light from distant quasars is absorbed as it passes through the cluster. These methods have provided tantalizing hints, but the full picture remains incomplete. Some researchers even speculate that the missing baryons could be hiding in the form of dark galaxies so faint they're nearly invisible to our instruments. The implications of this mystery are profound. If a significant fraction of ordinary matter is missing, it challenges our understanding of how galaxies and clusters form and evolve. It also raises questions about the distribution of matter in the universe and whether our current models need revision. Could the missing baryons be hiding in plain sight, or are they lurking in regions of space we've yet to explore? As the search continues, the missing baryon problem serves as a reminder of how much we still have to learn about the cosmos. It's a puzzle that not only deepens our curiosity, but also drives us to refine our tools and theories. And with each new discovery, we inch closer to solving one of the Virgo cluster's most enduring mysteries. Next, we'll delve into the ghostly dark galaxies of the Virgo cluster, where light is scarce and dark matter reigns supreme. Now, let's turn our attention to one of the most enigmatic discoveries in the Virgo cluster, the ghostly dark galaxies. These mysterious structures are unlike anything we're used to seeing in the cosmos. Unlike typical galaxies, which shine brightly with stars and gas, dark galaxies emit almost no light. Instead, they are composed primarily of dark matter, the invisible substance that makes up most of the universe's mass. Their discovery has opened up a new frontier in our understanding of galaxy formation and evolution. Dark galaxies were first theorized to exist decades ago, but it wasn't until recent advancements in observational technology that astronomers began to detect them. Using sensitive radio telescopes and other cutting-edge instruments, scientists have identified faint signals that hint at the presence of these elusive structures. These galaxies are so dim that they often go unnoticed, blending into the cosmic background. Yet, their gravitational influence on surrounding matter reveals their hidden presence. One of the most intriguing aspects of dark galaxies is their composition. While ordinary galaxies are filled with stars, gas, and dust, dark galaxies appear to lack these components almost entirely. Instead, they are dominated by dark matter, which doesn't emit, absorb, or reflect light. This raises a fascinating question: how do such galaxies form in the first place? Some theories suggest they could be failed galaxy structures that began to form stars but were somehow halted, leaving behind a dark matter skeleton. Others propose they might be remnants of ancient galaxies that lost their gas and stars over billions of years. the discovery of dark galaxies also challenges our understanding of the universe's structure. If these galaxies are as common as some scientists believe, they could play a significant role in the cosmic web, the vast network of matter that connects galaxies across the universe. Their presence might help explain why some regions of space seem to have more gravitational pull than can be accounted for by visible matter alone, but the mysteries don't end there. Dark galaxies could also hold clues about the nature of dark matter itself. By studying their behavior and distribution, astronomers hope to learn more about this elusive substance and how it shapes the universe. For instance, do dark galaxies interact with ordinary galaxies, or do they exist in isolation? And what role do they play in the evolution of galaxy clusters like Virgo? As we continue to explore these ghostly structures, one thing is clear: dark galaxies are a reminder of how much we still have to learn about the cosmos. They challenge our assumptions and push the boundaries of our knowledge, offering a tantalizing glimpse into the hidden side of the universe. Next, we'll uncover the secrets of the Virgo Cluster's intracluster light, a faint glow that reveals the hidden history of this cosmic neighborhood. Now, let's shift our gaze to a subtle yet fascinating phenomenon in the Virgo Cluster, the faint glow of intracluster light. This ethereal illumination, often overlooked, is the ghostly light that fills the spaces between galaxies in the cluster. Unlike the bright stars and glowing gas within galaxies, this light is diffuse and faint, requiring powerful telescopes to detect. But don't let its subtlety fool you. This glow holds secrets about the cluster's past and its intricate structure. Intracluster light is thought to originate from stars that have been stripped away from their home galaxies. These stars, once part of bustling galactic neighborhoods, are now adrift in the vast emptiness between galaxies. But how do stars end up in such a lonely existence? The answer lies in the violent interactions that occur within galaxy clusters. As galaxies move through the cluster, they can collide, merge, or pass close to one another, creating gravitational forces strong enough to pull stars out of their original galaxies. Over time, these orphan stars accumulate, creating a faint, widespread glow that permeates the cluster. This light isn't just a cosmic curiosity, it's a window into the history of the Virgo Cluster. By studying its distribution and intensity, astronomers can piece together the cluster's evolutionary story. For instance, areas with brighter intracluster light may indicate regions where galaxy interactions were more frequent or intense. This helps scientists map out the cluster's dynamic past, revealing how it has grown and changed over billions of years. But the mysteries don't stop there. Intracluster light also provides clues about the cluster's dark matter distribution. Since dark matter influences the motion of galaxies and stars, the way intracluster light is spread out can hint at where dark matter is concentrated. This makes it a valuable tool for understanding the invisible scaffolding that holds the cluster together. One of the most intriguing questions about intracluster light is its composition. Are these stars similar to those in galaxies, or do they have unique properties? Some studies suggest that intracluster stars might be older and less metal-rich than stars in galaxies, offering a glimpse into the early stages of galaxy formation. Others propose that these stars could have formed in the intracluster medium itself, a possibility that challenges our understanding of star formation. As we continue to study this faint glow, it's clear that intracluster light is more than just a cosmic afterthought. It's a vital piece of the puzzle, helping us understand the complex interactions and history of the Virgo Cluster. And as our telescopes grow more advanced, we're likely to uncover even more about this elusive phenomenon. Next, we'll explore the puzzling existence of ultra-diffuse galaxies in the Virgo Cluster, galaxies so faint and spread out that they defy our expectations of what a galaxy should be. Now, let's turn our attention to one of the most baffling inhabitants of the Virgo Cluster, ultra-diffuse galaxies. These galaxies are unlike anything you might picture when you think of a typical galaxy. Imagine a galaxy as large as the Milky Way, but with only a fraction of its stars, spread so thin that it becomes almost invisible against the backdrop of space. That's the essence of an ultra-diffuse galaxy, vast in size, yet so faint that they were only discovered in recent years thanks to advancements in telescope technology. What makes these galaxies so puzzling is their survival in the Virgo Cluster, one of the densest and most chaotic regions in the nearby universe. In such an environment, galaxies are constantly jostling and colliding, with gravitational forces tearing them apart. Yet, ultra-diffuse galaxies persist, their delicate structures somehow enduring the chaos. How do they manage to survive in such a hostile environment? This question has left astronomers scratching their heads. One theory suggests that ultra-diffuse galaxies might be protected by an unusually high amount of dark matter. Dark matter, the invisible substance that makes up most of the universe's mass, could provide a gravitational shield, holding these galaxies together despite the intense forces around them. However, not all ultra-diffuse galaxies show signs of having this protective dark matter halo, adding another layer of mystery to their existence. Another possibility is that these galaxies are the remnants of larger galaxies that were stripped of their stars and gas over time. As they pass through the cluster, interactions with other galaxies or the cluster's hot gas could have gradually eroded their material, leaving behind only a faint, ghostly outline. But if that's the case, why do some ultra-diffuse galaxies still appear to have a significant amount of gas, which should have been stripped away in such a dense environment? The faintness of these galaxies also raises questions about their star formation. With so few stars, ultra-diffuse galaxies are often referred to as failed galaxies, as they seem to have missed the opportunity to form the bustling stellar populations seen in other galaxies. Yet, some of these galaxies show signs of ongoing star formation, defying expectations and suggesting that they might still be active in ways we don't fully understand. Studying ultra-diffuse galaxies is like piecing together a cosmic puzzle. Each discovery brings new questions, challenging our understanding of how galaxies form and evolve. Their existence in the Virgo Cluster, a place where galaxies are constantly interacting and evolving, makes them a unique laboratory for testing our theories about galaxy survival and evolution. As we continue to explore these enigmatic galaxies, one thing is clear: they are more than just faint smudges in the night sky. They are windows into the complex and dynamic processes that shape the universe. And with every observation, we come closer to unraveling the secrets of these ghostly giants. Next, we'll delve into the mysterious X-ray cavities found in the Virgo Cluster, massive voids in the cluster's hot gas that hint at the powerful forces at work within this cosmic neighborhood. Now, let's shift our focus to another fascinating mystery within the Virgo Cluster, its X-ray cavities. These massive voids observed in the cluster's hot gas are like cosmic bubbles carved out of the surrounding material. But what could possibly create such enormous structures in one of the most densely packed regions of the universe? The answer might lie in the powerful forces unleashed by supermassive black holes. At the heart of many galaxies in the Virgo Cluster, including the famous M87, supermassive black holes are known to be active, devouring matter and releasing tremendous amounts of energy. As these black holes feed, they don't just consume, they also expel. Jets of high-energy particles are launched at nearly the speed of light, carving out vast cavities in the surrounding gas. These jets are so powerful that they can push the hot gas aside, creating voids that can span tens of thousands of light years. But the story doesn't end there. These X-ray cavities are not just empty spaces, they are dynamic regions filled with magnetic fields and high-energy particles. The energy injected by the black hole's jets can heat the surrounding gas, preventing it from cooling and forming new stars. This process, known as feedback, plays a crucial role in regulating the growth of galaxies and the cluster itself. Without it, the Virgo Cluster might look very different today. Yet, despite our understanding of how these cavities form, many questions remain. For instance, why do some cavities appear to be perfectly symmetrical, while others are irregular and distorted? What determines the size and shape of these voids, and how do they evolve over time? These are just a few of the puzzles that astronomers are working to solve. One intriguing possibility is that the cavities might be influenced by the cluster's complex magnetic fields or the turbulent motions of the gas itself. Alternatively, interactions between multiple black holes in the cluster could create overlapping cavities, leading to more complex structures. Each observation brings new clues, but also new challenges, as the sheer scale and energy involved in these phenomena push the limits of our current understanding. The study of X-ray cavities in the Virgo cluster is more than just an exploration of cosmic voids. It's a window into the interplay between supermassive black holes and their surroundings. These cavities reveal the immense power of black holes to shape their environments, influencing the evolution of entire galaxies and clusters. And as we continue to study them, we gain deeper insights into the forces that govern the universe on the largest scales. Next, we'll explore the peculiar motions of dwarf galaxies in the Virgo cluster, where their unexpected behavior challenges our understanding of gravity and dark matter. Now, let's turn our attention to a phenomenon that has left astronomers scratching their heads: the peculiar motion of dwarf galaxies in the Virgo cluster. These small, faint galaxies, often considered the building blocks of larger structures, are behaving in ways that defy our expectations. Instead of moving in predictable orbits, many dwarf galaxies in the cluster appear to be zipping around at speeds and trajectories that don't align with our current understanding of gravity and dark matter. At the heart of this mystery is the role of dark matter, the invisible substance that makes up a significant portion of the universe's mass. According to our models, dark matter should act as a cosmic scaffold, guiding the motion of galaxies within clusters like Virgo. But observations of dwarf galaxies in this region suggest something is off. Some of these galaxies are moving faster than predicted, while others seem to be following paths that don't match the gravitational pull of the cluster's visible matter. This discrepancy raises a critical question. Is our understanding of dark matter incomplete, or are there other forces at play that we haven't yet accounted for? One possibility is that the Virgo cluster's complex environment is influencing these dwarf galaxies in unexpected ways. The cluster is a bustling hub of activity, filled with hot gas, magnetic fields, and the gravitational pull of hundreds of galaxies. Interactions between these elements could be altering the motion of dwarf galaxies, creating the unusual patterns we observe. For example, collisions or close encounters with larger galaxies might give these smaller galaxies a gravitational kick, sending them on erratic paths. Another intriguing idea is that the distribution of dark matter in the Virgo cluster might be more uneven than we thought. If dark matter is clumped in certain areas or arranged in ways that differ from our models, it could explain why dwarf galaxies are moving so unpredictably. Alternatively, there might be unknown interactions between dark matter and ordinary matter that we haven't yet discovered. These possibilities highlight just how much we still have to learn about the invisible forces shaping our universe. The peculiar motion of dwarf galaxies isn't just a curiosity, it's a challenge to some of the most fundamental principles of astrophysics. If our understanding of gravity and dark matter is incomplete, it could have far-reaching implications for how we interpret the cosmos. Every observation of these galaxies brings us closer to unraveling the mystery, but it also reminds us of the complexity and wonder of the universe we're trying to understand. As we continue to study these enigmatic motions, we're not just exploring the behavior of dwarf galaxies, we're probing the very fabric of the universe itself. Next, we'll delve into another fascinating feature of the Virgo cluster: the sharp temperature drops known as cold fronts, and the mysteries they hold about the cluster's history and dynamics. Now, let's shift our focus to a phenomenon that feels almost like a cosmic weather event: the mysterious cold fronts of the Virgo Cluster. Imagine a vast ocean of hot gas, millions of degrees in temperature, swirling between galaxies. Within this seething expanse, astronomers have discovered something unexpected: sharp, sudden drops in temperature, like icy patches in a boiling sea. These are the cold fronts, and they're as puzzling as they are fascinating. At first glance, the idea of cold fronts in space might seem strange. After all, space is often thought of as a vacuum, devoid of weather as we know it. But the Virgo Cluster is anything but empty. It's filled with a thin, superheated gas that permeates the space between galaxies. This gas, heated to extreme temperatures by the cluster's intense gravitational forces, should theoretically be uniform in temperature. Yet, observations reveal regions where the temperature plunges dramatically, creating these cold fronts. So, what causes these temperature drops? One leading theory suggests that cold fronts are the result of cosmic collisions. When smaller galaxy groups or subclusters merge with the Virgo Cluster, they can create shockwaves that ripple through the hot gas. These shockwaves compress and cool the gas, forming the sharp temperature boundaries we observe. Think of it like a stone dropped into a pond. The ripples spread out, creating patterns that linger long after the initial impact. In the case of the Virgo Cluster, these ripples are cold fronts, lasting for billions of years. But here's where it gets even more intriguing. Cold fronts aren't just fleeting features, they're remarkably stable. Despite the chaotic environment of the cluster, with its swirling gas and gravitational turbulence, these cold fronts maintain their structure over vast stretches of time. This stability defies expectations, as the hot gas surrounding them should, in theory, erode or dissipate these cooler regions. Yet they persist like ancient relics of past cosmic events. The mystery deepens when we consider what these cold fronts reveal about the Virgo Cluster's history. Each cold front is like a snapshot of the cluster's dynamic past, preserving clues about the collisions and interactions that shaped it. By studying their shapes, sizes, and locations, astronomers can piece together a timeline of the cluster's evolution. But questions remain. Why do these cold fronts last so long? What mechanisms keep them intact in such a turbulent environment? And could they hold secrets about the behavior of hot gas in other galaxy clusters? As we explore these questions, we're not just uncovering the story of the Virgo Cluster, we're gaining insights into the fundamental processes that govern the universe. Cold fronts remind us that even in the most extreme environments, there are patterns and structures waiting to be understood. Next, we'll turn our attention to another enigmatic feature of the Virgo Cluster: the strong and complex magnetic fields that weave through its galaxies, shaping their evolution in ways we're only beginning to comprehend. Now, let's venture into another captivating mystery of the Virgo Cluster: its powerful and intricate magnetic fields. These invisible forces weave through the cluster, shaping the behavior of galaxies and the hot gas between them in ways that continue to baffle scientists. Unlike the magnetic fields we're familiar with on Earth, which are relatively straightforward, the magnetic fields in the Virgo Cluster are far more complex and enigmatic. Imagine a vast, invisible web stretching across the cluster, influencing everything it touches. These magnetic fields are incredibly strong, often millions of times more powerful than Earth's magnetic field. They permeate the space between galaxies, threading through the superheated gas and even extending into the galaxies themselves. But here's the puzzling part: we don't fully understand how these magnetic fields formed or what sustains them over such vast distances. One theory suggests that these magnetic fields could be remnants of the early universe, amplified over billions of years by the motions of gas and galaxies within the cluster. As galaxies move and collide, their interactions might generate electric currents, which in turn create and strengthen magnetic fields. Another possibility is that supermassive black holes at the centers of galaxies play a role, ejecting jets of charged particles that could seed and amplify these fields. Yet, despite these ideas, the exact origins of the Virgo cluster's magnetic fields remain a mystery. What makes these magnetic fields even more fascinating is their impact on galaxy evolution. They can influence how galaxies form stars, how gas flows between them, and even how cosmic rays travel through the cluster. For example, magnetic fields can slow down the collapse of gas clouds, delaying star formation in some galaxies. They can also channel and accelerate particles, creating cosmic rays that ripple through the cluster. In essence, these magnetic fields are like invisible sculptors, shaping the structure and behavior of the Virgo cluster in profound ways. But the story doesn't end there. The complexity of these magnetic fields also poses challenges for astronomers. Measuring them is no easy task, as they don't emit light or other forms of radiation directly. Instead, scientists rely on indirect methods, such as observing how they affect the polarization of light from distant galaxies or the behavior of cosmic rays. These observations have revealed that the magnetic fields in the Virgo cluster are not uniform. They vary in strength and direction, creating a patchwork of forces that add another layer of intrigue to this cosmic puzzle. As we continue to study these magnetic fields, we're not just uncovering the secrets of the Virgo cluster, we're gaining insights into the fundamental forces that shape the universe. They remind us that even in the vastness of space, invisible forces are at work, guiding the evolution of galaxies and the cosmos itself. Next, we'll explore another mystery that challenges our understanding of the Virgo cluster, the surprising scarcity of supernova, and what it might tell us about the life cycles of stars in this dense galactic neighborhood. Now, let's turn our attention to a cosmic mystery that has left astronomers scratching their heads: the surprising scarcity of supernova in the Virgo cluster. Supernova, the explosive deaths of massive stars, are some of the most dramatic events in the universe. They light up the cosmos, outshining entire galaxies for a brief moment, and play a crucial role in seeding the universe with heavy elements. Yet, in the Virgo cluster, these spectacular events seem to be far less common than scientists would expect. Why is that? To understand this puzzle, let's first consider what we know about supernova. In a typical galaxy, a supernova occurs roughly once every 50 to 100 years. Given the sheer number of galaxies in the Virgo cluster, around 2,000, you'd expect to see a steady stream of these cosmic fireworks. But observations tell a different story. The number of supernova detected in the cluster is significantly lower than predicted, leaving astronomers to wonder what's causing this discrepancy. One possible explanation lies in the unique environment of the Virgo cluster. It's an incredibly dense region, packed with galaxies that are constantly interacting and colliding. These interactions can strip galaxies of their gas, the raw material needed to form new stars. Without a steady supply of gas, fewer massive stars are born, and consequently, fewer supernova occur. In other words, the cluster's bustling galactic neighborhood might be stifling star formation, leading to a shortage of supernova. Another theory points to the age of the galaxies in the Virgo cluster. Many of these galaxies are older and have already exhausted their supply of massive, short-lived stars, the kind that end their lives in supernova. Instead, they're dominated by smaller, longer-lived stars that don't explode but fade away quietly. This shift in stellar populations could explain why supernova are rarer in the cluster than in younger, star-forming regions of the universe. There's also the possibility that we're simply missing some supernova. Detecting these explosions in a cluster as vast and crowded as Virgo is no easy task. Some supernova might be obscured by dust or hidden behind other galaxies, making them harder to spot. Additionally, the light from these explosions can be diluted by the cluster's immense size, reducing their apparent brightness and making them more challenging to detect with current telescopes. But the mystery doesn't end there. The scarcity of supernova in the Virgo cluster could have broader implications for our understanding of galaxy evolution and the life cycles of stars. Supernovae are not just spectacular events, they're also cosmic recyclers, spreading elements like iron, oxygen, and carbon into space, which eventually form new stars, planets, and even life. If supernovae are less common in clusters like Virgo, it could mean that the chemical evolution of these regions is slower or different than in other parts of the universe. As astronomers continue to study this phenomenon, they're using advanced telescopes and simulations to piece together the puzzle. By observing the cluster in different wavelengths of light and tracking the movements of its galaxies, they hope to uncover the reasons behind the missing supernova. Each discovery brings us closer to understanding not just the Virgo cluster, but the intricate processes that shape galaxies across the cosmos. Next, we'll delve into another enigmatic feature of the Virgo cluster, the elusive dark matter filaments that are thought to connect its galaxies, and the challenges scientists face in detecting these invisible threads. Now, let's shift our focus to one of the most intriguing mysteries in the Virgo cluster, the elusive dark matter filaments that are believed to weave through this cosmic neighborhood, connecting its galaxies like invisible threads. Dark matter, the mysterious substance that makes up about 85% of the universe's mass, doesn't emit light or interact with electromagnetic forces, making it nearly impossible to observe directly. Yet, its presence is felt through its gravitational influence, shaping the structure of the universe on the largest scales. In the Virgo cluster, scientists suspect that dark matter forms a vast network of filaments, creating a cosmic web that links galaxies together. These filaments are thought to act as highways, guiding the flow of gas and galaxies as they move through the cluster. But detecting these invisible threads is no easy task. Unlike galaxies or gas clouds, dark matter doesn't emit any light, so astronomers have to rely on indirect methods to study it. One approach involves observing the gravitational effects of dark matter on visible matter. For example, when light from distant galaxies passes near a dark matter filament, its path is bent by the filament's gravity, a phenomenon known as gravitational lensing. By carefully analyzing these distortions, scientists can map the distribution of dark matter and infer the presence of filaments. However, this method is incredibly challenging in a dense environment like the Virgo cluster, where the gravitational influence of galaxies and gas clouds can complicate the picture. Another technique involves studying the motion of galaxies within the cluster. If dark matter filaments are present, they should influence how galaxies move, creating subtle patterns in their velocities. By tracking these movements, astronomers hope to uncover the hidden structure of the filaments. But again, the crowded and dynamic nature of the Virgo cluster makes this a daunting task, as interactions between galaxies can obscure these subtle signals. The difficulty in detecting dark matter filaments isn't just a technical challenge, it's also a fundamental one. Dark matter's elusive nature means that we still don't fully understand its properties or how it behaves on cosmic scales. Are the filaments smooth and continuous, or do they have a more complex, clumpy structure? How do they interact with ordinary matter, and what role do they play in the evolution of galaxies? These are questions that continue to puzzle scientists. Despite the challenges, the search for dark matter filaments in the Virgo cluster is a crucial part of understanding the universe's large-scale structure. These filaments are thought to play a key role in the formation and evolution of galaxy clusters, acting as the scaffolding upon which galaxies are built. By unraveling their secrets, we could gain new insights into how the universe grew from a nearly uniform soup of matter after the Big Bang into the intricate web of galaxies we see today. As astronomers refine their techniques and develop new tools, the hope is that we'll one day be able to see these invisible threads more clearly. Advanced telescopes like the upcoming James Webb Space Telescope and next-generation ground-based observatories could provide the precision needed to map the dark matter web in unprecedented detail. Each step forward brings us closer to solving the enigma of dark matter filaments and unlocking the mysteries of the cosmos. Next, we'll explore another fascinating aspect of the Virgo cluster: the mysterious gamma-ray emissions that have been detected within its boundaries, and what they might reveal about the nature of dark matter and other exotic phenomena. Now, let's turn our attention to another eerie mystery lurking within the Virgo cluster, its ghostly gamma-ray emissions. These high-energy bursts of light, invisible to the human eye, have been detected emanating from the cluster, leaving scientists both intrigued and puzzled. Gamma rays are the most energetic form of light in the universe, often produced by extreme cosmic events like supernova, black hole jets, or the annihilation of matter and antimatter. But in the Virgo cluster, the source of these emissions remains shrouded in mystery, sparking debates about their origins and what they might reveal about the cosmos. One leading theory suggests that these gamma rays could be linked to dark matter, the elusive substance that makes up the majority of the universe's mass. Some models propose that dark matter particles, when they collide, could annihilate each other, releasing gamma rays as a byproduct. If this is the case, the gamma-ray emissions from the Virgo cluster could provide a rare glimpse into the nature of dark matter itself. However, detecting such signals is incredibly challenging, as gamma rays can also be produced by more mundane astrophysical processes, like the interactions of cosmic rays with gas clouds. Another possibility is that these emissions are tied to the cluster's supermassive black holes. The Virgo cluster is home to numerous galaxies, many of which harbor these gravitational giants at their centers. As matter falls into a supermassive black hole, it can heat up and emit high-energy radiation, including gamma rays. But the distribution and intensity of the emissions observed in the Virgo cluster don't always align with what we'd expect from black hole activity alone, leaving room for alternative explanations. Some researchers have even speculated that the gamma rays could be the result of exotic phenomena we've yet to fully understand. For instance, they might be produced by the decay of hypothetical particles predicted by theories beyond the standard model of particle physics. These particles, if they exist, could offer clues about the fundamental nature of the universe and the forces that govern it. The challenge in unraveling this mystery lies in the complexity of the Virgo cluster itself. With its dense population of galaxies, gas clouds, and dark matter, pinpointing the exact source of the gamma rays is no small feat. Astronomers rely on advanced instruments like the Fermi Gamma Ray Space Telescope to detect and map these emissions, but even with cutting-edge technology, the data can be difficult to interpret. What makes this phenomenon particularly fascinating is its potential to bridge the gap between astrophysics and particle physics. If the gamma rays are indeed linked to dark matter or exotic particles, they could provide a unique window into the hidden workings of the universe. On the other hand, if they stem from more conventional sources, they could still shed light on the extreme environments within the Virgo cluster and the processes that drive its evolution. As scientists continue to study these ghostly emissions, they're not just searching for answers, they're also refining our understanding of the universe's most enigmatic components. Each observation brings us closer to uncovering the truth behind these high-energy signals, whether they're tied to dark matter, black holes, or something entirely unexpected. And as we'll see next, the Virgo cluster has even more secrets to reveal, including the peculiar behavior of its so-called red and dead galaxies. Now, shifting our gaze to another cosmic puzzle, we encounter the so-called red and dead galaxies of the Virgo cluster. These galaxies, which appear to have ceased forming new stars, stand out as stark anomalies in a universe teeming with vibrant, star-forming regions. Their reddish hue, a telltale sign of aging stellar populations, contrasts sharply with the blue light emitted by younger, more active galaxies. But why have these galaxies stopped producing stars, and what does this mean for our understanding of galaxy evolution? At first glance, the answer might seem straightforward. Galaxies run out of gas literally. The raw material needed to form new stars, primarily hydrogen gas, can be depleted over time. However, the Virgo cluster's environment complicates this explanation. The cluster is a densely packed region where galaxies frequently interact and collide. These interactions should, in theory, trigger bursts of star formation by compressing gas clouds and igniting new stellar nurseries. Yet many galaxies in the Virgo cluster remain eerily quiet, their star-forming engines seemingly shut down. One leading hypothesis points to the cluster's intense gravitational forces. As galaxies move through the Virgo cluster, they encounter the hot, diffuse gas that fills the space between them. This gas, heated to millions of degrees, exerts a pressure that can strip away the cooler gas within galaxies' gas that would otherwise fuel star formation. This process, known as ram pressure stripping, effectively starves galaxies of their star-forming material, leaving them red and dead. Another factor could be the role of supermassive black holes. Many galaxies in the Virgo cluster host these gravitational behemoths at their centers. When a black hole becomes active, it can release vast amounts of energy, heating the surrounding gas and preventing it from cooling and collapsing into stars. This feedback mechanism, while crucial for regulating galaxy growth, might also push some galaxies into a state of permanent dormancy. Interestingly, the red and dead galaxies in the Virgo cluster challenge our expectations of how galaxies evolve. In less dense environments, galaxies tend to follow a more predictable life cycle, transitioning from star forming to quiescent over billions of years. But in the Virgo cluster, this process appears to be accelerated, with galaxies shutting down star formation much earlier than anticipated. This raises questions about the role of environment in shaping galaxy evolution and whether similar processes are at work in other galaxy clusters. The mystery deepens when we consider the diversity of galaxies within the Virgo cluster. Not all galaxies are red and dead. Some continue to form stars, albeit at a slower rate, while others exhibit signs of recent interactions that have reignited their star-forming activity. This variation suggests that multiple factors, environmental, gravitational, and internal, are at play, each influencing a galaxy's fate in different ways. As astronomers continue to study these enigmatic galaxies, they're not just uncovering the secrets of the Virgo cluster, they're also refining our understanding of galaxy evolution as a whole. The red and dead galaxies serve as cosmic laboratories, offering insights into the processes that can halt star formation and transform vibrant galaxies into quiet relics of the universe's past. And as we'll soon discover, the Virgo cluster holds even more surprises, including the curious case of its missing dwarf galaxies. Now, let's turn our attention to another intriguing mystery lurking within the Virgo cluster, the case of its missing dwarf galaxies. Dwarf galaxies, as their name suggests, are smaller, fainter cousins of larger galaxies like our Milky Way. They're thought to be the building blocks of the universe, forming early in cosmic history and merging over time to create the grand spiral and elliptical galaxies we see today. Yet, when astronomers peer into the Virgo cluster, they find far fewer dwarf galaxies than their models predict. This discrepancy has sparked a cosmic detective story, with scientists scrambling to uncover where these elusive galaxies might be hiding, or why they never formed in the first place. Theories abound to explain this puzzling shortage. One possibility is that dwarf galaxies are simply harder to detect than their larger counterparts. Their faint light can easily be drowned out by the glare of brighter galaxies or the diffuse glow of the cluster's hot gas. Advanced telescopes and observational techniques have helped uncover some of these hidden dwarfs, but even with these tools, the numbers still fall short of predictions. This suggests that the issue isn't just about visibility, it's something more fundamental. Another explanation points to the harsh environment of the Virgo cluster itself. Dwarf galaxies, with their relatively small masses, are particularly vulnerable to the cluster's intense gravitational forces. As they move through the cluster, they can be torn apart by tidal forces, their stars scattered into the intracluster medium. This process, known as tidal disruption, could effectively erase dwarf galaxies from existence, leaving behind only faint streams of stars as evidence of their former presence. Alternatively, some researchers propose that the missing dwarfs never formed in the first place. The Virgo Cluster's dense environment might have suppressed the formation of these smaller galaxies early in the universe's history. The high temperatures and pressures in the cluster's gas could have prevented the collapse of small gas clouds, stunting the growth of dwarf galaxies before they even had a chance to shine. Adding another layer to the mystery, some dwarf galaxies might have been absorbed by larger galaxies through mergers. Over billions of years, these smaller galaxies could have been drawn into the gravitational embrace of their more massive neighbors, their stars and gas becoming part of the larger galaxy's structure. While this process would explain the absence of some dwarfs, it doesn't fully account for the sheer scale of the discrepancy observed in the Virgo cluster. The search for these missing dwarfs isn't just an academic exercise. It has profound implications for our understanding of galaxy formation and the role of dark matter. Dwarf galaxies are thought to be rich in dark matter, making them key players in testing theories about its distribution and behavior. If they're truly missing, it could mean that our models of dark matter or galaxy formation need significant revision. As astronomers continue to probe the Virgo cluster with ever more sensitive instruments, they're inching closer to solving this cosmic puzzle. Whether the missing dwarfs are hiding in plain sight, destroyed by the cluster's harsh environment, or never formed at all, their absence challenges our understanding of the universe on a fundamental level. And as we'll soon see, the Virgo cluster has even more surprises in store, including the curious case of its runaway galaxies. Now, let's shift our gaze to another fascinating enigma within the Virgo cluster, the so-called runaway galaxies. These are galaxies that seem to be racing through the cluster at astonishing speeds, defying expectations and leaving scientists puzzled about what could be propelling them. Unlike the more predictable motions of most galaxies, these cosmic speedsters appear to be on a trajectory that suggests they've been flung outward by some immense force. But what could possibly cause a galaxy to move so fast? One leading theory points to the gravitational interactions within the cluster itself. The Virgo cluster is a densely packed region, teeming with galaxies that are constantly tugging and pulling on one another due to their immense gravitational influence. In some cases, a close encounter between two galaxies could result in one being slingshotted away at incredible speeds. This process, known as gravitational slingshotting, is similar to how spacecraft gain speed by swinging around planets. However, the sheer scale of this phenomenon in the Virgo cluster is mind-boggling, as it involves entire galaxies being hurled across vast cosmic distances. Another possibility is that these runaway galaxies were once part of smaller groups or clusters that merged with the Virgo cluster. During such mergers, the chaotic gravitational forces at play could have ejected certain galaxies at high velocities, sending them careening through space. This would explain why some galaxies appear to be moving so much faster than their neighbors, as if they've been cast out from their original homes. But the mystery deepens when we consider the role of dark matter. The distribution of dark matter in the Virgo cluster is thought to play a crucial role in shaping the motions of galaxies. If the dark matter halo surrounding the cluster is uneven or has unusual features, it could create gravitational anomalies that accelerate certain galaxies to extreme speeds. This raises intriguing questions about the nature of dark matter itself and how it interacts with the visible universe. Adding to the intrigue, some runaway galaxies show signs of being stripped of their gas and stars as they race through the cluster. The intense pressure of the intracluster medium, combined with their high speeds, can strip away the material that would otherwise form new stars, leaving these galaxies as faint, ghostly remnants of their former selves. This process, known as ram pressure stripping, further complicates the picture, as it suggests that these galaxies are not only moving fast but also undergoing dramatic transformations as they travel. The study of runaway galaxies isn't just about solving a cosmic mystery. It's about understanding the forces that shape the universe on the largest scales. By unraveling the secrets of these high-speed galaxies, scientists hope to gain new insights into the dynamics of galaxy clusters, the behavior of dark matter, and the processes that drive galaxy evolution. And as we continue to explore the Virgo cluster, each discovery brings us closer to piecing together the grand puzzle of the cosmos. Next, we'll delve into another captivating phenomenon, the mystery of the Virgo cluster's blue straggler stars, which defy expectations by appearing younger than their surroundings. Now, let's turn our attention to a stellar mystery that defies the natural order of aging in the cosmos, the enigmatic blue straggler stars of the Virgo cluster. These peculiar stars stand out like cosmic anomalies, glowing with a youthful blue hue that starkly contrasts with the older, redder stars surrounding them. At first glance, they seem to break the rules of stellar evolution, appearing far younger than their neighbors. But how can stars in such a densely populated cluster, where most stars are billions of years old, suddenly appear so vibrant and youthful? The answer lies in a fascinating interplay of cosmic collisions and stellar rejuvenation. One of the leading theories suggests that blue stragglers are the result of stellar collisions or mergers. In the crowded environment of the Virgo cluster, stars often come into close contact, and sometimes they even collide. When two stars merge, their combined mass can reignite nuclear fusion processes, creating a new, hotter, and more luminous star that appears younger than its actual age. This process essentially gives the star a second lease on life, transforming it into a blue straggler. It's like two aging stars joining forces to create a single, rejuvenated powerhouse. Another intriguing possibility is that blue stragglers form through mass transfer in binary star systems. In these systems, two stars orbit each other closely, and over time, one star can siphon material from its companion. This transfer of mass can rejuvenate the receiving star, causing it to burn hotter and brighter, while the donor star fades into obscurity. This process not only explains the youthful appearance of blue stragglers, but also highlights the dynamic and often dramatic interactions that occur within binary systems. But the mystery doesn't end there. Some blue stragglers in the Virgo cluster appear to be isolated, with no obvious companion or evidence of a recent collision. This has led scientists to propose alternative explanations, such as the possibility that these stars were once part of triple or multiple star systems. In such systems, complex gravitational interactions could have ejected one star while leaving behind a rejuvenated blue straggler. This scenario adds another layer of complexity to the puzzle, as it suggests that the origins of these stars may be even more varied and intricate than previously thought. The study of blue stragglers isn't just about solving a cosmic riddle. It's about understanding the life cycles of stars and the processes that can alter their trajectories. These stars serve as a reminder that the universe is far from static. It's a dynamic, ever-changing environment where stars can be born, die, and even be reborn in unexpected ways. By unraveling the secrets of blue stragglers, scientists hope to gain deeper insights into the mechanisms of stellar evolution and the unique conditions that shape the Virgo cluster. As we continue to explore the Virgo cluster, each discovery brings us closer to understanding the intricate dance of stars within this cosmic neighborhood. Next, we'll delve into another puzzling phenomenon, the mystery of the Virgo cluster's missing intergalactic gas, and what its absence might reveal about the evolution of galaxies. Now, shifting our gaze to another cosmic enigma, we encounter the puzzling case of the Virgo cluster's missing intergalactic gas. In the vast expanse of this galaxy cluster, scientists have long expected to find a substantial amount of gas floating between galaxies, gas that plays a crucial role in the formation and evolution of galaxies. Yet, when they measured the amount of this intergalactic gas, they found it to be far less than predicted. This discrepancy has left astronomers scratching their heads, wondering where this gas has gone and what its absence means for our understanding of the universe. Intergalactic gas, often referred to as the intracluster medium, is a hot, diffuse plasma that fills the spaces between galaxies in a cluster. It's not just empty space. This gas is a reservoir of raw material that can fuel the birth of new stars and galaxies. In the Virgo cluster, however, a significant portion of this gas seems to have vanished. One possible explanation is that the gas has been heated to such extreme temperatures that it becomes invisible to our current observational tools. When gas is heated to millions of degrees, it emits X-rays, but if it's too hot or too diffuse, it can slip past our detection methods, effectively becoming missing from our measurements. Another intriguing theory suggests that the missing gas might have been stripped away by the intense gravitational forces within the cluster. As galaxies move through the cluster, they can drag gas out of their surroundings, leaving behind a trail of depleted material. This process, known as ram pressure stripping, is particularly effective in dense environments like the Virgo cluster. Over billions of years, this stripping could have significantly reduced the amount of gas available between galaxies, creating the deficit we observe today. But the mystery deepens when we consider the implications of this missing gas for galaxy formation. Without sufficient intergalactic gas, galaxies in the Virgo cluster may struggle to form new stars, effectively stalling their growth. This could explain why many galaxies in the cluster appear red and dead, with little to no ongoing star formation. The absence of this gas also challenges our models of how galaxy clusters evolve over time, forcing scientists to rethink the processes that govern the distribution and behavior of matter in the universe. Some researchers have proposed that the missing gas might have been consumed by supermassive black holes at the centers of galaxies. These black holes are known to devour surrounding material, releasing enormous amounts of energy in the process. If a significant amount of intergalactic gas has been funneled into these black holes, it could explain both the missing gas and the intense activity observed in some of the cluster's galaxies. However, this theory is still under investigation, and the true fate of the missing gas remains an open question. The search for answers continues, with astronomers using advanced telescopes and simulations to trace the movement and distribution of gas within the Virgo cluster. Each new observation brings us closer to understanding this cosmic puzzle, shedding light on the complex interplay of forces that shape the evolution of galaxy clusters. As we unravel the mystery of the missing intergalactic gas, we gain not only a clearer picture of the Virgo cluster, but also deeper insights into the fundamental processes that drive the universe's grand design. With this mystery still lingering, let's now turn our attention to another fascinating phenomenon, the Virgo cluster's ghostly radio relics and the clues they might hold about ancient cosmic collisions. Now, as we venture further into the mysteries of the Virgo cluster, we encounter a phenomenon that seems almost otherworldly: the cluster's ghostly radio relics. These faint, sprawling structures, detected through radio waves, stretch across vast distances within the cluster, resembling ghostly echoes of some long-forgotten cosmic event. But what exactly are these radio relics, and what secrets do they hold about the history of the Virgo cluster? Radio relics are enormous, arc-shaped structures that emit radio waves, often found on the outskirts of galaxy clusters. They are thought to be the remnants of ancient cosmic collisions, violent encounters between galaxy clusters that occurred billions of years ago. When two clusters collide, the immense energy released can accelerate particles to nearly the speed of light, creating shock waves that ripple through the surrounding gas. These shock waves, in turn, generate the radio emissions we observe as relics. In the Virgo cluster, these relics are particularly intriguing because they appear to be much older and more diffuse than those found in other clusters, earning them the nickname ghostly. One of the most puzzling aspects of these relics is their sheer size. Some of them span hundreds of thousands of light years, dwarfing even the largest galaxies in the cluster. How such massive structures formed and why they have persisted for so long remains a mystery. One theory suggests that the relics are the result of multiple collisions over billions of years, with each event adding to the complexity and scale of the structures. Another possibility is that the relics are fueled by the ongoing activity of supermassive black holes, which inject energy into the surrounding gas, creating shock waves that sustain the radio emissions. But the mysteries don't end there. The exact mechanisms behind the formation of these relics are still poorly understood. For instance, why do some relics appear as sharp, well-defined arcs, while others are more diffuse and spread out? And how do these structures manage to retain their shape over such vast timescales, despite the chaotic environment of the cluster? These questions challenge our understanding of the physics governing galaxy clusters and the forces that shape their evolution. Adding to the intrigue is the possibility that these relics might hold clues about the distribution of dark matter in the Virgo cluster. Some researchers believe that the shock waves responsible for creating the relics could also influence the behavior of dark matter, potentially leaving behind subtle signatures in the relic structure. If true, studying these relics could provide new insights into the elusive nature of dark matter and its role in the formation of galaxy clusters. As astronomers continue to study these ghostly radio relics, they are using some of the most advanced radio telescopes in the world, such as the Low-Frequency Array and the Very Large Array, to map their structure and trace their origins. Each new observation brings us closer to unraveling the secrets of these ancient cosmic echoes, shedding light on the violent history of the Virgo cluster and the forces that have shaped it over billions of years. With the enigma of the radio relics still unfolding, let's now turn our attention to another captivating mystery: the unusual properties of the Virgo cluster's dark matter halo, and how it challenges our understanding of the invisible scaffolding that holds the universe together. Now, shifting our gaze to the invisible yet dominant force shaping the Virgo cluster, we delve into the mystery of its dark matter halo. Dark matter, the elusive substance that makes up most of the universe's mass, is thought to form vast, invisible halos around galaxy clusters, acting as a cosmic scaffold that holds galaxies together. But the dark matter halo surrounding the Virgo cluster is anything but ordinary. It defies expectations and raises profound questions about our understanding of this mysterious material. Unlike the smooth, evenly distributed halos predicted by simulations, the Virgo cluster's dark matter halo appears to be clumpy and uneven. Observations suggest that the distribution of dark matter within the halo is far more complex than previously thought, with dense pockets and sparse regions scattered throughout. This irregularity challenges the standard model of dark matter, which assumes a more uniform distribution. What could be causing these anomalies? Some scientists propose that interactions between dark matter and ordinary matter, or even between dark matter particles themselves, might be responsible. Others suggest that the halo's structure could be influenced by the cluster's turbulent history of collisions and mergers, which may have disrupted the dark matter's arrangement over billions of years. Adding to the intrigue is the halo's sheer size. The Virgo cluster's dark matter halo extends far beyond its visible galaxies, enveloping the entire cluster in an invisible web of gravitational influence. Yet, despite its vast scale, the halo's mass doesn't align neatly with the observed motions of galaxies within the cluster. Some galaxies move faster than expected, while others seem to lag behind, hinting at a mismatch between the predicted and actual distribution of dark matter. This discrepancy has led researchers to question whether our current models of dark matter are incomplete, or if there's something fundamentally different about the Virgo cluster's halo compared to others. One particularly puzzling aspect is the halo's interaction with the cluster's hot gas. Observations show that the gas, which fills the space between galaxies, doesn't always follow the gravitational pull of the dark matter halo. In some regions, the gas appears to move independently, as if influenced by forces beyond the halo's reach. This behavior suggests that the dark matter halo might not be as dominant as we once believed, or that other factors, such as magnetic fields or cosmic rays, are playing a significant role in shaping the cluster's dynamics. The mystery deepens when we consider the halo's potential connection to dark matter, filaments, the cosmic threads thought to link galaxy clusters across the universe. Some researchers speculate that the Virgo cluster's halo might be intertwined with these filaments, creating a complex network of dark matter that extends far beyond the cluster itself. If true, studying the halo could provide valuable insights into the larger structure of the cosmic web and the role dark matter plays in connecting the universe's largest structures. As astronomers continue to probe the Virgo cluster's dark matter halo using advanced telescopes and simulations, they are uncovering more questions than answers. Each new discovery challenges our assumptions and pushes the boundaries of our understanding, reminding us just how much we have yet to learn about the invisible forces shaping the cosmos. With this enigma still unfolding, let's now turn to another fascinating mystery, the puzzling absence of star clusters in the Virgo cluster and what it might reveal about the cluster's turbulent past. Now, as we venture into another layer of the Virgo cluster's mysteries, we encounter a curious absent star clusters that seem to have vanished without a trace. Star clusters, those glittering collections of stars bound together by gravity, are typically abundant in galaxy clusters like Virgo. Yet, when astronomers peer into this cosmic neighborhood, they find far fewer of these stellar gatherings than predicted. This puzzling shortage has sparked a wave of scientific inquiry as researchers scramble to uncover what might be causing this unexpected void. One leading theory points to the Virgo cluster's chaotic environment. As one of the densest regions in the nearby universe, the cluster is a hotbed of gravitational interactions, with galaxies frequently colliding or passing close to one another. These violent encounters can tear apart star clusters, scattering their stars into the vast expanse of intergalactic space. Over billions of years, this relentless tug of war could have significantly reduced the number of star clusters we observe today. It's a cosmic game of survival where only the most resilient clusters endure. Another possibility lies in the cluster's intense radiation fields. The Virgo cluster is filled with hot gas and energetic particles, which can strip away the outer layers of star clusters, leaving them vulnerable to disintegration. Over time, this process could erode the clusters, causing them to fade from view. Some scientists even suggest that the cluster's supermassive black holes might play a role, as their powerful jets and outflows could disrupt nearby star clusters, further contributing to their disappearance. But the mystery doesn't end there. Some researchers propose that the missing star clusters might not be missing at all. They could simply be hiding in plain sight. It's possible that many of these clusters are too faint or diffused to be detected with current telescopes, blending into the background of the cluster's luminous galaxies. If true, this would mean our observations are incomplete, and future advancements in telescope technology could reveal a wealth of previously unseen star clusters. Adding another layer to the puzzle is the role of dark matter. While dark matter doesn't emit light, its gravitational influence could shape the distribution and survival of star clusters. If the Virgo cluster's dark matter halo is as clumpy and uneven as recent observations suggest, it might create pockets of intense gravitational forces that either destroy star clusters or push them into regions where they're harder to detect. This interplay between dark matter and star clusters remains a tantalizing area of study, offering new avenues to explore the cluster's hidden dynamics. As astronomers continue to investigate this enigma, they're not just searching for missing star clusters, they're piecing together the story of the Virgo cluster's evolution. Each discovery brings us closer to understanding how these cosmic structures form, interact, and change over time. And with that, we turn our attention to the final mystery in our journey, the Virgo Cluster's intricate connection to the cosmic web and how this vast network shapes its destiny. Now, as we step into the grand finale of our exploration, we find ourselves gazing at the Virgo Cluster's place within the cosmic web, a vast, intricate network of galaxies, gas, and dark matter that stretches across the universe. This cosmic web is the backbone of the cosmos, a sprawling structure that connects galaxy clusters like Virgo to their neighbors, shaping the universe on the largest scales imaginable. But how exactly does the Virgo cluster fit into this cosmic tapestry, and what mysteries does this connection hold? At the heart of this phenomenon lies the cluster's gravitational pull. The Virgo cluster, with its immense mass, acts as a gravitational anchor, drawing in galaxies, gas, and even other clusters over billions of years. This process doesn't happen in isolation. It's part of a larger dance orchestrated by the cosmic web. Thin filaments of dark matter and gas stretch between clusters, acting like cosmic highways that guide the flow of matter across the universe. The Virgo cluster sits at the intersection of several of these filaments, making it a key player in the web's structure. But here's where the mystery deepens. While we can map the cosmic web on a broad scale, the finer details of how the Virgo cluster interacts with these filaments remain elusive. For instance, how does the cluster's immense gravity affect the flow of gas and galaxies along these filaments? And what role do the cluster's supermassive black holes play in shaping these interactions? Some scientists believe that the energy released by these black holes could heat the surrounding gas, altering its movement and even disrupting the delicate balance of the cosmic web in the cluster's vicinity. Another intriguing question is how the Virgo cluster's dark matter halo interacts with the web. Dark matter, though invisible, is the cosmic web's primary architect, weaving the filaments that connect clusters. Observations suggest that the Virgo cluster's dark matter halo might be more complex than previously thought, with clumps and irregularities that could influence how matter flows into and out of the cluster. This raises the possibility that the cluster's dark matter is not just a passive participant but an active force in shaping its cosmic environment. Adding to the intrigue is the cluster's role in the larger story of the universe's evolution. The cosmic web is not static. It's a dynamic structure that evolves over time, driven by the gravitational pull of clusters like Virgo. As the cluster grows, it pulls in more matter, altering the web's structure and influencing the formation of galaxies and clusters around it. This interplay between the Virgo cluster and the cosmic web offers a window into the universe's past, present, and future, revealing how the largest structures in the cosmos are interconnected. Yet, despite these insights, many questions remain. How do the cluster's interactions with the cosmic web affect the formation of stars and galaxies within it? And what can these interactions tell us about the nature of dark matter and dark energy, the mysterious forces driving the universe's expansion? These are the questions that keep astronomers awake at night, driving them to peer deeper into the cosmos in search of answers. As we conclude our journey through the Virgo cluster's mysteries, we're reminded that the universe is far more interconnected than we often realize. The cosmic web is not just a backdrop, it's a living, evolving network that binds everything together from the smallest galaxies to the largest clusters. And the Virgo cluster, with its unique place in this web, offers us a glimpse into the grand design of the cosmos, inviting us to keep exploring, questioning, and marveling at the wonders that lie beyond our reach. Now, let's take a closer look at how the cosmic web continues to shape the Virgo cluster's evolution, revealing even more layers of mystery. The cosmic web isn't just a static framework, it's a dynamic force that actively influences the cluster's growth and behavior over billions of years. One of the most fascinating aspects of this relationship is how the web's filaments act as conduits, funneling gas and galaxies into the Virgo cluster. This process isn't random, it's a carefully orchestrated flow driven by gravity, with the cluster acting as a cosmic magnet, pulling in matter from its surroundings. But what happens when this flow encounters the cluster's intense gravitational field? Observations suggest that the gas streaming into the Virgo cluster doesn't simply merge smoothly. Instead, it often collides and heats up, creating shockwaves that ripple through the cluster's atmosphere. These shockwaves can trigger bursts of star formation in some regions while stifling it in others, adding another layer of complexity to the cluster's evolution. Scientists are still trying to understand how these interactions affect the overall structure of the Virgo cluster and whether they could explain some of the unusual features we've observed, like its massive radio halo or the peculiar motions of its dwarf galaxies. Another intriguing question is how the cosmic web influences the cluster's dark matter distribution. Dark matter, as we've discussed, is the invisible scaffolding that holds the web together. But within the Virgo cluster, this dark matter isn't evenly spread. It forms clumps and filaments that mirror the larger structure of the cosmic web. These clumps could be key to understanding how the cluster's gravity interacts with the web on smaller scales. For instance, do these dark matter structures act as cosmic traffic controllers, guiding the flow of gas and galaxies into the cluster? Or do they create pockets of resistance that disrupt the flow, leading to the formation of unusual features like the cluster's X-ray cavities? The cosmic web also plays a role in the Virgo cluster's interactions with its neighbors. The cluster isn't an isolated entity, it's part of a larger network that includes other galaxy clusters and groups. The web's filaments connect these structures, allowing them to exchange matter and energy over vast distances. This interconnectedness raises questions about how the Virgo cluster's evolution is influenced by its cosmic neighbors. For example, could collisions with other clusters along these filaments explain some of the cluster's unexplained phenomena, like its runaway galaxies or the mysterious gamma-ray emissions detected in its vicinity? As we explore these questions, we're reminded that the Virgo cluster is more than just a collection of galaxies. It's a living, evolving system shaped by its place in the cosmic web. Every observation we make, every mystery we uncover, brings us closer to understanding how the largest structures in the universe are connected. Yet, for every answer we find, new questions arise. How do the cluster's interactions with the web affect the formation of stars and galaxies within it? And what can these interactions tell us about the nature of dark matter and dark energy, the forces driving the universe's expansion? These are the questions that drive astronomers to keep exploring, to keep pushing the boundaries of our knowledge. The Virgo cluster, with its intricate ties to the cosmic web, offers us a unique window into the universe's grand design. And as we continue to study it, we're reminded that the cosmos is a place of endless wonder, where every discovery leads to new mysteries waiting to be unraveled. As we bring our journey through the Virgo cluster to a close, it's clear that this cosmic neighborhood is a treasure trove of mysteries, each one offering a glimpse into the profound complexities of our universe. From the baffling absence of dark matter in certain galaxies to the enigmatic gamma-ray emissions that hint at unseen forces, the Virgo cluster challenges our understanding of the cosmos at every turn. These 25 unexplained phenomena aren't just scientific curiosities, they're keys to unlocking the secrets of dark matter, galaxy formation, and the very fabric of space itself. Each discovery we've explored today raises new questions, pushing the boundaries of what we know and inspiring astronomers to dig deeper. Whether it's the peculiar motions of dwarf galaxies, the ghostly glow of intracluster light, or the mysterious radio relics echoing ancient cosmic collisions, the Virgo cluster reminds us that the universe is far stranger and more wondrous than we can imagine. These mysteries aren't just puzzles for scientists, they're invitations for all of us to marvel at the vastness of space and our place within it. So, what do you think about these cosmic enigmas? Which phenomenon left you the most intrigued? Let us know in the comments below. We'd love to hear your thoughts and theories. And if you enjoyed this deep dive into the mysteries of the Virgo cluster, don't forget to hit that like button, subscribe to our channel, and ring the notification bell so you never miss out on our next cosmic adventure. The universe is full of wonders waiting to be uncovered, and we can't wait to explore them with you. Until next time, keep looking up. The stars have so much more to reveal.